where you, me, and my houseplants will have some fun doing math. Today is a special day. Today is Pi Day. Why do we celebrate Pi Day? Well, let's start by looking at what pi is and looking at some reasons why we think it's so cool. So to start off with, imagine taking any circle. The circumference of the circle is the perimeter or the length around the circle. So here I have it drawn in purple. The diameter of the circle is the length from one side to the other going straight through the middle. So the largest or longest length you can draw through the circle touching both sides. Pi, our constant pi, is defined to be the ratio of the circumference divided by the diameter. So pi is equal to circumference over diameter. And this is true for any circle. So here we've used a pi to demonstrate pi because it's Pi Day, but this works for any circle we choose. But that's maybe not interesting enough to require a whole day to celebrate it. So why are mathematicians so obsessed with this concept of pi? Well, today I wanted to show you a couple examples where pi shows up where we don't really expect it to. And kind of to emphasize that that's why it's so cool, is that we have this constant that we have been spending many hundreds of years trying to calculate. The ancient Babylonians were trying to calculate this value. The ancient Egyptians used pi to create the pyramids. So since humans have been around and trying to do mathematics, they've been trying to figure out the mysteries hidden behind this value. So let's start with a little example. Suppose you take some number, we'll call it a, and we'd like to know what divides a, or what is a divisible by. Well, we can look at the probabilities. So there is a 100% probability that a is divisible by 1, because every number is divisible by 1. So we say that it has a probability of 1. Now, what is the probability that a is divisible by 2? So assuming that a is some random integer number, think of all of the integers. Well, 1 is not divisible by 2, but 2 is, and 3 isn't, but 4 is. And we notice that every second number is divisible by 2. And so we say that for 2, there is a 50% chance that a is divisible by 2. So we write that in fraction form as 1/2. What is the probability that a is divisible by 3? Well, again, we can look at our numbers. 1, 2, 3 is divisible by 3. 4, 5, 6 is divisible by 3. 7, 8, 9 is divisible by 3. And we see that every third number has this property, and therefore there is a 1 in 3 chance that a is divisible by 3. And we can keep going with this idea. So for some random number p, there is a 1 in p chance that a is divisible by that value. We say that a is prime if it's only divisible by 1 in itself. So we say that the only factors of a, the only things that divide into a, are itself and 1. Suppose we choose another number. Let's choose another number b. Then we will say that a and b are CoPrime if they do not share any divisors other than 1, or they don't share any factors other than 1. So another way we can think of it is we can say that if we make a fraction a over b, then that fraction would be as reduced as possible. So let's look at an example. The numbers 15 and 8 are CoPrime because 15 is divisible by 1, 3, 5, and 15, whereas 8 is divisible by 1, 2, 4, and 8. So they don't share any values when you look at their factors, and therefore we say they're CoPrime. If we look at the number 12, 12 is not CoPrime with either of those examples because it shares a factor of 3 with 15 and a factor of 4 and 2 with 8. So what does this have to do with pi? Well, the interesting thing is that the probability, remember we were talking about probability of a number being divisible by another number, the probability that a and b are CoPrime, meaning the probability or the chance that they do not share any factors, is 6 over pi squared. And now this is a strange and interesting and unexpected result. right? We know that pi has to do with circles, but what does pi have to do with numbers being co-prime? What does pi have to do with division? So we see that pi shows up in places that we aren't expecting it to, which is why we are so intrigued by this value. So if we were to go and prove this fact that I've just given you, we're not going to prove it, but if we were going to prove it, we would need to use something called the Basal problem. So the Basal problem is a problem that was solved by Euler many years ago. Euler is from Basel, which is why we give this problem this name. Also, we've named too many things after Euler to keep naming things after him. If I take the number 1 and I add to it 1 over 4, and I add to that 1 over 9, and I add to that 1 over 16, and then 1 over 25, and I keep adding these values, well, first of all, do you notice the pattern here? We're adding 1 over a square. So it's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. And Euler has proven for us that this summation, if we go on forever, if we keep adding 1 over squared numbers all the way for all of the numbers, then this series will converge to pi squared over 6. So again, what business does pi have being in this kind of series? I've added up 1 over square numbers and we ended up with a value with pi in it. Again, we're not going to do any proofs here today, but if you would like to look at a really interesting explanation for this problem, I will link the 3 blue, 1 brown video that goes over this using lighthouses, and they prove why this is true. It's a really great video. I recommend you check that out. One other strange place that we find pi showing up is when we're looking at area. At some point you learned that the area of a circle is equal to pi r squared, where r is the radius or half of the diameter. But we already know pi shows up when we're looking at circles. Here's an interesting example where pi shows up where we don't expect it to. So imagine I take this function, 1 over x squared plus x plus 1. And I look at the area under the curve from x equals 1 to x equals infinity. So we would imagine that since this is an infinite length, we should get an infinite area. But we don't. So we can calculate the area of this by taking the integral from 1 to infinity. And we get a really interesting result. The area under this curve, or the integral from 1 to infinity, is equal to the square root of 3 over 9 times pi. So again, we're looking at the area of something that is not a circle. It's actually what appears to be infinite, and we're getting pi showing up again. Another integral example is called the Gauss integral. If we take the function e to the minus x squared and we look at the area under the curve, where the curve goes out infinitely in either direction, so we're taking it from minus infinity to positive infinity, and we calculate the area under the curve, or the integral from minus infinity to positive infinity of this function, then we get the square root of pi. Which again is an interesting result. Like, why would that be? I hope you enjoyed this quick video, and I hope that you are as excited about pi as I am. Enjoy your pi day, do some math, eat some pie, have a wonderful day, and thank you so much for watching.